Most computers do not look like traditional computers. They are hidden away inside mechanical equipment, operating out of sight and often unrecognized. This Kodak digital camera is a prime example. Behind the lens and shutter button lies a dedicated system engineered strictly for image capture and processing. These vintage printers rely on similar internal systems to manage complex paper paths and printhead timing, routines that must be executed with high precision. In technical terms, an embedded system is a microprocessor-based system designed to control, monitor, or assist a larger, complete device. Unlike a desktop PC, which can execute a nearly infinite variety of programs, these systems are fixed. They are built for a single, dedicated function that remains unchanged throughout their lifecycle. The physical brain behind these systems is the microcontroller unit, or MCU. You can see the distinct pin layout on this ATmega 1609 chip. Because they must operate inside everyday tools, embedded architectures are entirely dictated by strict physical, economic, and functional constraints. To understand modern hardware engineering, we have to look at the specific limitations that forced engineers to rethink computing architecture from the ground up. This technical triangle defines the boundaries of the field. Every design choice is a trade-off between cost, physical size, and available power. The single-functioned nature of these systems means they must execute one specific task flawlessly and repeatedly for decades. From a manufacturing perspective, the electronics must be cheap enough for consumer markets and small enough to fit on a single chip without requiring cooling fans. Power consumption is equally vital. Devices like this Palm Pilot illustrate the challenge of sustaining processing on a fixed battery budget. Furthermore, these systems must be reactive. In an automotive braking system, the hardware must ingest environmental data and respond to it in real time. Standard desktop microprocessors cannot meet all these requirements simultaneously, necessitating the creation of a unified system on silicon. This macroscopic view of an IC die reveals the internal complexity of a microcontroller. It integrates the CPU, memory, and peripherals into this single layout. Let's map out the conceptual architecture of this system on a chip. The CPU block is the core logic unit. It is responsible for fetching, decoding, and executing the program instructions. Next is the ROM or flash memory, where the program instructions are permanently stored. Modern flash can withstand up to 300,000 erase cycles. For temporary storage during program execution, the architecture includes a RAM block for volatile data. EEPROM is also integrated to save permanent data that must survive when the power is turned off. Finally, peripheral blocks are added along the edges: timers for signals, AD converters for sensors, and I/O ports for communication. This monolithic integration provides the speed, cost efficiency, and low power draw to meet embedded design constraints. Designing and programming millions of transistors on this scale is a massive task. How do engineers manage this level of complexity? The answer lies in structured design and design partitioning. By utilizing hierarchy, engineers can treat complex circuits as black boxes with well-defined interfaces, hiding the minute details of individual components. Consider a radio system. It is easier to view it as a tuner, an amplifier, and a power supply, rather than hundreds of individual transistors and resistors. This is formalized in the Y chart, a framework that allows designers to describe a system across 3 separate domains. The behavioral domain covers the algorithms and mathematical equations that dictate the system's intended function. The structural domain defines the architecture, mapping out the logic gates, registers, and counters that execute those behaviors. Finally, the physical domain focuses on the actual transistor placement and silicon layout. This top-down abstraction allows engineers to simulate the entire design and verify it works before any hardware is actually manufactured. Once we understand how these systems are designed, we can look at how they are categorized in the real world. The first major classification is based on performance and functional requirements. Real-time systems are those where correctness depends on hitting specific timing deadlines. These range from hard deadlines in avionics to firm in banking and soft in video stemming. Standalone systems like this TiVo video recorder function independently. They process local digital or analog inputs and drive their own displays and storage. Networked systems connect to LANs or the internet to access shared resources. This is the fastest growing sector of the market. Mobile systems are portable electronics such as phones and digital cameras that operate within rigid memory and power ceilings. A second way to classify these systems is by the scale of the microcontroller itself. This scale ranges from small-scale 8-bit chips to sophisticated systems that use 32-bit RISC processors or reconfigurable FPGAs. This taxonomy is what allows engineers to select the exact hardware architecture required for a specific task. Embedded systems are the dedicated platforms that run our modern world. This RepRap 3D printer requires an embedded system to translate digital code into precise mechanical motion. By integrating the CPU, memory, and I/O onto a single monolithic chip, engineers overcome the limitations of space, cost, and power. Using abstraction tools like the Y chart, Ray can manage the immense complexity of silicon design from the top down. These systems are then strictly categorized based on their timing requirements, connectivity, and processor performance. Looking ahead, we see a shift from isolated standalone controllers toward complex multiprocessor environments. These invisible computers are expanding beyond individual devices to become the structural, intelligent backbone of our modern.
Let's study more and like, share, and subscribe for such more content. And comment something you want to learn.